Energy is involved in a lot of chemical reactions, and it's also involved in a lot of physical changes too, because how do you go from a solid ice cube to liquid water? You put heat into it, right? You heat it up and that causes it to melt. So we need to understand a little bit about energy. So one way to define energy is that it is the capacity to do work. So then we say, well, what is work? Because there are a lot of words that we use in science and we use in everyday life, but they don't always mean exactly the same thing, right? Everyday life, we think work is going to that place that maybe we're not so happy to go, but they give us money for staying there, right? That's not the kind of work we're talking about. In science, work is defined as the action of a force through a distance. So here's my water bottle on the counter. And if I put force on it and push it across the bench, I just did work. Anybody gonna pay me for that? No, they're not. But that's what work is. So here's a guy pushing a big box across the floor. That's work. If he stands here and pushes on the box but it doesn't move, there has been no through a distance and no work has been done. So energy is the capacity to do work. There are many, many different types of energy. The two broad categories are kinetic energy. That's not what I meant to do. Highlighter. Kinetic energy and potential energy. Kinetic energy is the energy associated with motion. So there's a major called kinesiology. That's the study of motion of the human body, right? Kinetic energy is about the motion of objects and the energy that they have because of that. Potential energy is associated either with the position of an object or with its composition. So here we have an object with high potential energy. It's this 10 kilogram weight, and it's kind of teetering on top of a tall building. It's unstable. You give it a little nudge, and what's going to happen? It's going to fall off the building. The potential energy is because of the distance that this is raised above the ground. When released, it will fall to the ground because of gravity. And as it gets closer to the ground, its potential energy decreases, but its movement, its kinetic energy increases. So as this is falling, the potential energy that it had is being turned into kinetic energy. And it'll go faster and faster, assuming it doesn't get to terminal velocity in this short distance, and then it'll hit the sidewalk. And then where does all the energy go? It's not at all obvious. It goes into thermal energy of the sidewalk and to some extent the weight as well. Thermal energy, this guy right here, is the energy associated with the temperature of an object. And so it's actually a type of kinetic energy. The movement there is not that of this thing moving through space. The movement we're talking about is the individual atoms or molecules in that substance vibrating or wiggling. So I talked about the 3 states of chemistry students, right? What state are you guys in right now? Solid, liquid, or gas? Solid. And you're a crystalline solid because you're all sitting in nice rows. And everybody's, pretty chill, right? Not a lot of fidgeting going on. So you would be at a low temperature. You have low thermal energy because you're not wiggling around a lot. You could imagine if it was a group of kindergartners, right? And they've been sitting here for 10 minutes and they're just like, they're obeying you to sit in the chair, but they're like wiggling and they're just they want to get up and run around. That's higher kinetic energy. The particles aren't moving relative to each other, but they're moving. And that type of movement is thermal energy, another type of kinetic energy. So as this weight hits the ground, the kinetic energy of moving through space is gone, but that impact causes all of the atoms and molecules in the vicinity to do a lot of jostling, and that's where the energy gets dissipated as heat. We mentioned the law of conservation of mass on Tuesday. There is an accompanying law called the law of conservation of energy. And this states that energy is neither created nor destroyed. Law of conservation of mass says mass is neither created nor destroyed. So the total energy that something has is the sum of its kinetic energy and its potential energy. Energy can change from one form to another, as we saw with the weight falling off the building. Potential energy was turning into kinetic energy. Energy can also flow from one object to another object. But when those things happen, the total quantity of energy is the same. We're not creating or destroying energy. Objects that have high potential energy tend to be unstable. So like, something heavy sitting at the edge of a high building. It's unstable. You give it a little nudge and it'll fall off. That same object sitting on the sidewalk is not as unstable, right? Because when you're on the ground, it's hard to fall off the ground, right? There's no more down to go. You can give it a nudge and it's just going to move it over a little bit. But high potential energy is unstable, and those things will tend to change in a way that reduces their potential energy. Chemical energy is a type of potential energy, but instead of coming from its position above the ground, it comes from the electrostatic forces between all the different charged particles that make up the atoms and molecules. So because of those forces, something like gasoline, which we use to burn and give a lot of energy to power the car, right? Where's the energy come from? Well, it comes from potential energy due to the instability of the molecules. They will easily react with oxygen to lower their energy. Well, energy cannot be created or destroyed. That energy has to go somewhere. Where does it go? It comes out as heat energy. When you burn gas, it's hot. That happens with natural gas too, or propane, right? Why do you have propane and burn it in your gas grill? Because it gives off heat so that you can cook your steaks, right? So in physical or chemical changes, energy will always be conserved. There is a place where energy is not conserved, and that is in a nuclear reaction, right? But we're not doing nuclear chemistry in 1A. But part of me feels like I just need to give you the fine print. In a physical or chemical change, it is conserved. So I mentioned this already. Systems with high potential energy tend to change in a direction that lowers their potential energy, and that releases the energy that they did have into the surroundings. Here we have a picture of a gasoline-powered car. In the fuel tank, we have gasoline, which has a lot of chemical potential energy because those molecules are unstable. When we bring that gasoline into the engine and ignite it, it undergoes a chemical reaction and explodes and releases the energy that it had into mostly thermal energy, and will cause the pistons in the car to move, and the mechanics of the car translate that into rolling your wheels, and your car goes forward. What happens to the temperature of the engine as the engine runs? It gets hot, right? You have a radiator there and a cooling system to keep it cooler from getting too hot. But if that's not functioning, it will get too hot and you can actually ruin your engine. All of that heat is energy that came from the gasoline. It's not all usable. right? So we use some of the energy in that explosion to push the pistons, but a lot of the energy is lost, not meaning that it's destroyed, but it dissipates and is not useful to us, dissipates as heat. And the molecules from the gasoline, they form other compounds during combustion, and then those come out of the exhaust. These molecules are lower in potential energy. They are much more stable than the gasoline. So some of this released energy is harnessed to do work. The car moves forward. Some of the energy just dissipates into heat. Anybody have any questions?